Hello, everyone, and welcome to our webinar on wireless charging for unmanned aerial systems. Let me start by introducing the speakers. First, my name is Mohammed Abdurazik, and I'm a PhD student at NC State University Freedom System Center, and I'm mainly interested in multi-objective optimization of power converters, wireless power transfer, and resonant converters. And I'll be presenting part one and part two of this webinar. Second, my colleague Hatif Abdul Majid bin Abdul Majid, PhD, also PhD student, and his research interest is mainly DC microgrid design and control, wireless power transfer, and control systems. Hatif will be presenting the third and final part of this webinar. And lastly, this is Dr. Pantic, our advisor. He's an associate professor at NC State University. His research interests span power electronics for electric transportation, resonant power converters, wired and wireless charging systems, pressure-tolerant electronics, personal mobility and micromobility, and magnetic circuit designs. Now let me walk you through the outline of this presentation. We'll start with an introduction um, about wireless charging in general, and then dive into the concept of inductive power transfer, which is central to this presentation. Next, we'll talk about the types of unmanned aerial systems or drones and their applications, industrial and other applications. And then we'll talk about wireless charging specifically for drone applications and multi-objective optimization in relation to that, and also system modeling on objective functions or optimization criteria to consider while working on wireless charging systems for drones. Also, we'll present some optimization results on a case study or a project that we worked on. And lastly, Hatif will be presenting this last part, which is experimental results and field deployment of this case study. Wireless charging has a fascinating history. And it all started with the great inventor Nikola Tesla. Tesla was a pioneer in wireless charging and or wireless power transfer in the sense that he actually tried to apply this and commercialize this. In the late 19th century and early 20th century, he experimented with transmitting power using radio frequency resonant transformers, which are famously called Tesla coils now. He even gave some public demonstrations where he lit a light bulb across the stage using wireless charging or wireless power transfer, and without using any physical connections. And these demonstrations actually captured the imagine, fascinated many people. But unfortunately, Tesla was not successful at commercializing this technology at his time. However, this principle in his demonstrations uh, showed the concept of resonant inductive coupling, and is now widely adopted in modern wireless charging systems. Today, it forms the foundation of wireless charging in devices like smartphones, electric vehicles, and even drones. And this will be the focus of our presentation in later slides. Let us now move on to the concept of inductive power transfer. So wireless charging has many applications. In figure one here, we see an electric vehicle, which is one of the most prominent applications of wireless charging. Using wireless charging in this application eliminates the need of plug-in cables and it makes the EV charging experience more convenient and user-friendly. In figure 2 here, it shows an automated guided vehicle, or AGV, and which is they are widely used in warehouses and factories. Wireless charging allows these vehicles to operate efficiently without any downtime, which is critical in warehouses, and without manual recharging. Figure 3 here shows an example where wireless charging is applied and can be applied further, which is personal mobility devices like e-scooters and e-bikes, for example. Moving to figure 4, we see a breakthrough application in biomedical implants, such as pacemakers and other electronic devices. Uh, Wireless power transfer eliminates the need for invasive surgeries, which may be needed to replace the batteries of these implants, improving patient care and safety in general, and also saving medical costs. Moving on to figure 5, which is an example of application in robotics, from industrial robotics to autonomous robotics in research. Wireless charging enables seamless and continuous operation of these autonomous robotic systems. And finally, one of the prominent examples, or most famous examples here, is smartphones, which are now commonly equipped. All high-end smartphones are commonly equipped with wireless charging capabilities, making charging simpler and easier. These examples are famous examples where wireless charging is applied, but they're not all but they don't cover the all applications of wireless charging. Uh, now, let's talk about the types of near-field wireless power transfer. Starting with so there are two types: inductive power transfer, or IPT, and capacitive power transfer, or CPT. First, in inductive power transfer, it relies on magnetic fields. So magnetic fields is the field which helps us transfer energy between the coils. Um, and it's the most widely used method in wireless power transfer today. And for example, IPT is used in wireless charging of electric vehicles, as I stated, smartphones, and biomedical plants. Um, One of the key advantages of IPT is its high efficiency, especially over distances measured in the centimeter scale. So it could be from 1 to several centimeters. However, a disadvantage is that the transmitter coil and receiver coil need to be aligned to improve the power transfer capability. And there are many solutions to tackle this issue. Next, we have capacitive power transfer, which uses the electric field to transfer between two plates to transfer energy. CPT is less common than IPT, but is being explored for very specific applications. So it's less common. CPT's main advantage is that it can work with the smaller, lighter components, or for smaller applications, which require very, very small gap between the transmitter plate and the receiving plate. One of its disadvantages is that it's even more sensitive to misalignment between the transmitting and receiving plates. So this is why it's not predominantly or commonly deployed in many applications like IPT. Let's now dive into the fundamentals of inductive power transfer. Let's start by looking at Faraday's law of induction, which states that a time-varying magnetic field induces an electric voltage in a nearby conductor. So in the context of inductive power transfer, this is how energy is transferred from a transmitter to the receiver coil. Secondly, we have Ampere's law, and this law can help us relate or uh, quantify the magnetic field generated by pushing current through a conductor. Moving on, one common example of an inductive power transfer circuit is a series compensated IPT system. This system is basically, this configuration is widely used because it improves the power transfer efficiency. In the series compensation, capacitors C1 and C2 are connected in series with both the transmitter and receiver coils L1 and L2. These capacitors help tune the system at the resonant frequency, which maximizes real power transfer and minimizes energy loss. It also reduces the reactive power or circulating power or useless power basically, and increases the real power or useful power in our case, which ends up being absorbed or transferred to the load R subload. We have some common quantities that we use to express the efficiency of the system. And these quantities here are the loaded quality factor, expressed in terms of L2, the angular frequency of the system, and R load. And we also have the the coils quality factors, QC1 and QC2. So in these next two expressions here, we have power transfer expressions that can be derived that expresses how much power is transferred to our load. And as you can see here, it's a function of the frequency, omega sub s, the transmitter current, or the primary side current, the mutual inductance, and the receiver inductance, and the receiver quality, loaded quality factor. It can also be expressed in terms of primary quantities like here. And so what do we learn from this power transfer expression for this circuit? We learned that if we increase the coupling factor here between the transmitter and receiver coils, we are able to transfer more power. A second expression we have here is the efficiency of the system, of this circuit that we see here. And it can be expressed as a function of the coupling coefficient K and the coils quality factors. In this expression, we can understand that we can maximize or increase the efficiency by increasing this product, which is a product of the K factor or coupling coefficient factor times the square root of the coils quality factors QC1 and QC2. So these are some preliminary equations that can help us understand and design a series compensated wireless charging system. On this slide here, we have a block diagram of a typical IPT system, and let me guide you through the key components. Starting with the inverter. The inverter converts DC voltage into a high-frequency AC current, which is essential for creating the time-varying magnetic field needed for power transfer. It operates at higher frequencies to improve the power transfer density, the power density and efficiency of the system. This frequency is typically in the tens of kilohertz, or in applications like electric vehicles, or higher power applications in general, and in the megahertz range in lower power applications. Next, we have the primary compensation tank or circuit, which plays several important roles. It acts as a reservoir for the reactive power, helping managing the coil inductance effectively and reactive power. It also filters the output current harmonics, improving the quality factor of the operating of the system's operation. And uh, Additionally, it shapes the inverter current, and it basically makes it purely sinusoidal after filtering higher harmonics. Now let us discuss the coils, which are the central part of an IPT system. The coils here are typically made of lit wire or stranded wire, and these types of wires are usually used to improve or reduce power losses caused by the skin and proximity effects, uh, and these effects manifest at higher frequencies. This is how we take care of them, by using lit wire. And we have ferrite materials or Fe materials that we can add to the coil assembly for several purposes. Some of these purposes is to help shape the magnetic field and focus the magnetic field. It also enhances power transfer capability by improving the coupling coefficient, and it suppresses any leakage field, and which is the same as focusing the magnetic field. Together, these components work, you can say, up to the transmitter coil. Together, these components form the primary side assembly, or the transmitter. Now let me continue with the secondary side of the IPT system, starting with the compensation tank. So the secondary coil usually or typically uses a compensation tank, which can be a parallel capacitor, series capacitor, like I showed earlier in an earlier slide, or a series capacitor followed by a parallel capacitor. And there are even more complex structures that can be used. And it all depends on the required specifications or characteristics of the that are required by the application. Uh, Followed by this compensation circuit or network, uh, we usually have a power conditioner. In this case, this block comprises a rectifier, followed by either an LC filter, a boost converter, or a buck converter. So in the case of an LC filter, this LC filter is needed to filter out the high frequency noise received from the receiver coil or transmitted from the receiver coil, and provide DC power or DC voltage or current. This DC power is essential because most loads like batteries and electronics use DC power. In the case if an LC filter is not present or is not used, a DC-DC converter is added after the rectifier. This DC-DC converter has a built-in filter that will filter out high frequency noise, and it will also condition this rectified voltage to either a higher voltage level by using a boost converter, or to a lower voltage level by using a buck converter. And this is also decided based on the requirements or the specifications of the load. So this is the typical block diagram of an IPT topology, in general terms. And this concludes the first part of this webinar. And I'll be continuing in the second part, mainly focusing on the application of inductive power transfer in unmanned aerial systems or drones. So I'll see you in the next video.